Well, bonjour à tous. Okay, that's the French. The amount of French I could use today. I'm in the process of learning, so I might come back in some years and be able to do the thing in French. My name is Giorgia Nadizar, and I am currently at the University of Trieste. Before talking to you about this, I will share a few words about myself. So I am a computer and electronics engineer by background, and then I moved for my PhD in data science and applied data science and AI. And I am currently a postdoc in Trieste, but from November 1st, I will be starting in Toulouse. So that's the reason why I will need to learn French. Concerning my research interests, it was all shaped by my background, let's say. So I started with automatic control and embodied AI, so AI in a robot, basically, because I was an engineer. Of course, these robots could be made in very different ways. And in my lab, we were big fans of using biological inspiration to make them work better. Did it work? A bit. So, of course, you need to optimize these things. And to do so, we relied on meteoristic optimization, mostly on evolutionary computation. And then I started to build an interest for interpretability. So, these things are very cool when they do what they should, but also you might want to know why they're making certain decisions and so on. So this is why I shifted my interest towards interpretability. And currently, let's say my main focus of research is on interpretable control, which lies more or less at the intersection of these big squares. So this is what I'm going to talk to you about today. So the title of the seminar is Interpretable Control Policies, what they mean. So I will try to more or less converge on a notion of interpretability with you, and also how we can optimize them, of course, with evolutionary computation. So I'm going to start with a bit of motivation, because I don't know if the viennoiserie were motivating enough. And then I will try to converge on a definition of interpretability, although that's not very easy, as we will see together. Then apply and show you how we can apply that to control. Of course, as any research, there will be some limitations and hopefully some directions to address these. And applications, actually one application that I will be focusing on in my future postdoc. So let me start with the motivation. So I don't really know your backgrounds, but I assume you're all data scientists or engineers. So I guess that you're aware that neural networks can do a lot of good things when it comes to decision making. And that could be in supervised learning, so for instance, classification, regression, and so on and so forth, but also in reinforcement learning and control. And the performances are in general super good. Like you can see these drones that were able to compete at superhuman level in a complicated competition, with obstacles and so on. I wouldn't be able to control it, so, ANNs can really do wonders at decision making. But of course, they come with a downside that you don't really have a clear understanding of what's going on inside of their decision making. So as you can see here, if we open the thing, there is a black box inside. There's not much we can understand directly. So what people started coming up with is, okay, we can't really understand this. Let's try to build something on top of it to explain it. And this is where XAI came from. So there was a growing interest in trying to figure out, in general, post-hoc, what was going on behind the decision-making. And this could be done both in supervised learning, but also in control, for different reasons. This was very good, but often not enough. You can have very different models, very different tools to explain your decisions, but these may not be enough, especially in certain settings, because these tools are great for exploration. They can indeed elucidate what's going on, but they often fail to provide a falsifiable explanation, which is key in certain settings, such as critical operation scenarios. So think of human lives being at stake, big amounts of money, energy, or the environment. And also in these cases, there are often regulations that you need to comply with. The bureaucracy is something that we need to really take into account. And so if we want to have an AI system that we can actually use in practice, making it interpretable, so for instance, verifiable, is something that can really help us to do so. So I hope that this was a bit convincing of why interpretability is a good, let's say, objective. But what is interpretability? Let's try to give a coarse definition of it as the ability of a user to deduce why a model is making a certain decision, of course, given enough time to analyze it. And this can be an inherent property of the model in general, as opposed to post hoc explanations, which in general you put on top of an existing model. And it hinges mostly on two properties. The first one being simulatability, so the fact that you can actually wrap your head around what is going on in the model when it comes to a decision, and also decomposability. So you can observe the model and be like, okay, this is a component, it's doing this and that, then there's this other thing, they cooperate this way, and then they come together to a decision. And this is a property that's, let's say, mostly common for human-built engineering systems, but not as much for instance, artificial neural networks. Another important element is transparency, for instance, because you need to observe and be able to understand, what's going on there. And of course, some representations are intrinsically more interpretable than others. This representation, a lot of numbers, connections. These two, okay, way better, but still it's subjective, A lot of people will like this one, but maybe some others, they know the numbers, they know that they mean certain things, and they're like, oh no, this one I actually like better for my application. So it's really subjective to any person of us, given our background and our personal preferences. So the first step I took in the interpretability direction was trying to capture how we perceive interpretability as different subjects. So this work was not done on robots. It was done on symbolic regression, which is I assume you know what that is, the idea that you need to find a formula to fit a certain data set, for instance. And in this case, we were trying to understand how different humans perceive mathematical equations as interpretable or not. So we had two objectives, which arguably are contrasting objectives. The first one being accuracy. Of course, you want your formulas to be precise, but also making them interpretable to a certain individual. So what we did to grasp the interpretability of a person, we trained an estimator for it, and it was a neural network. So what we did during the optimization process, so this is the evolutionary optimization loop, we sampled some formula from the population. I assume you guys are all familiar with evolutionary computation, right?
Mostly.
Yes. So I'm not going to go into the details of it. Let's say you can think it as something that iteratively optimizes solutions for a problem, let's see, and it's a group of solutions. So what we did, we sampled some formulas from the population, we call it, and we asked the person, okay, which one do you like best? Rank them. And according to these feedbacks, we were training an artificial neural network that was progressively learning how to rank formula for a given person. So this was the interpretability estimator. On the other hand, the other objective of the optimization was, of course, accuracy that you can measure with certain classic metrics like mean square error. And what we did, as I was saying, we sampled the formula from the population, which was evolving in order to move towards the distribution that would actually solve the problem. So we used active learning in order to keep improving in the distribution. And the interesting results that we found from this study was that, in fact, different users implied different outcomes. So that was some sort of confirmation for us that it was a good idea to estimate the subjective interpretability. So what we noted is that interpretability accuracy trade-off was different for different people. Because maybe I am a super engineer, so I am quite okay with understanding difficult formula. Maybe I don't have that much of a background in maths, so I need to keep things more down to earth. So this is what this slide will tell you, basically. Not going to go into too much details, but let's just keep this takeaway message from this one. These results before were done with simulated users, so we tried to simulate the preference giving mechanism. When we moved to actual people, the results were a bit less clear. So here we show in different colors the amount of people that preferred the model that was tailored for them in red, the people that were okay with both, and the people that actually preferred models that were trained with different estimators of interpretability, such as the size of a formula, which is something pretty obvious, or this other formula that was taken from the literature. And what we noted here is that in general, people were not always fans of the formula that were trained for them. Possibly because what happened is that these people we took, let's say, were not very into the problem. They didn't know the variables at stake. They didn't know, the real meaning of things. So they ended up being, whatever. And this was partly a negative result. But what's good from this is that in general, when we're doing our studies, for instance, on robots, we can also rely on coarse metrics of interpretability. We take the formula size, it's not going to be the perfect notion of interpretability, but as a first estimation, it's going to be fine. Or also what we can do is take this formula here, which was taken from a big user study on Reddit. I think it was more than 1,000 participants in the end. And it's going to estimate, by counting the number of different types of operations and stuff in the formula, how much people are prone to liking it. So this was the preliminaries on interpretability. Now, how we can move this into the domain of control. So when we have to control a robot, again, I don't know the backgrounds here. So very silly scheme. What we have when we control a robot, we have some sensors. We can have different things like memory, but let's disregard that for now. And we use the controller in order to have a mapping from the sensors to the actuators that tell us, okay, robot, you need to do this and that. Usually what happens is that we have a neural network here. For the drones that I've shown you before, it was a big neural network trained with deep reinforcement learning. What we want to do is have something that we can understand here. So for instance, one or multiple symbolic equations depending on the amount of actuators we have. So we want to change the paradigm. Although, small remark must be made, all of this is going to be in a dynamical system. Again, I don't know the details of the backgrounds here, but in this setting, an additional layer of complexity adds because there is the memory of the robots, like the physical memory, I mean, the fact that it can be like this or like that. So things can really change depending on the setting. But still, we're taking one step at a time. So in practice, we have our friend. He's going to have a bunch of inputs and outputs. I don't know if you can see, but like, for instance, the eyes let him see. Then he has to control his tiny arms and also the wheels. So what we want is to have, for instance, a graph that maps the inputs to the outputs, so that finally our robot can say hi to us, do these funny little things. So far, so good. I forgot to tell you before, but if you have any questions or think that there are things that I should clarify more, feel free to interrupt. Yes.
This is Cartesian genetic programming.
Yes. So thank you for the assist there.
It was either that or TPG, but
you do TPGs here. I wouldn't come here and teach you your own mechanism. So this is in fact Cartesian genetic programming, although you can also have other things to use this. So for instance, linear genetic programming can also be used, and it's more or less a key. So you guys are all familiar with TPGs, I guess?
He knows the name.
yes.
Somebody has been annoying you about them.
Yeah.
I'm under that impression. So now I'm here to annoy you about CGP instead. So I'm not, again, gonna teach you the nitty-gritty details about this. Just the take-home message here is that it's a mechanism with which you can evolve a graph. Given a bunch of nodes distributed on a Cartesian plane, this is why it's called Cartesian, you are going to evolve how each node behaves in terms of function. So each of these nodes will have a gene that encodes for the function in it, given a certain function library. So for instance, add, multiply, or subtract. And then you're also going to evolve the connections. So you see here, this one's connected to this one's to that, so on and so forth, for each of them. Plus, you're going to evolve the outputs. So from which of the graph nodes you're going to take your outputs from. And what can happen is that certain nodes here are not used. So that's pretty simple, let's say. And as I showed you, the amount of nodes is fixed. So what you have is a triplet of integers for each of the nodes, plus the amount of integers for the outputs. So you can simply evolve a graph with a sequence of numbers, which is also very convenient because you can parallelize on GPU in case you're interested in that. So, and yeah, to mutate the graph, you simply do in-flip mutation. So given the range of allowed integers for a certain position, you just say, okay, okay. So we're doing evolutionary policy search to optimize these graphs. So now a bit of background on evolution. So evolutionary computation, as I was saying before, is a mechanism with which you optimize solutions for a certain problem. What you do is you initialize your population, you initialize the genotypes. So in this case, the genotypes are the sequence of integers. Then you map them into the policies and you assess how these policies behave. Given this, you're going to select the good ones, usually, to make the parents. You mutate them, or you do variation. If you have multiple ones, you can also recombine them. You take the offspring and you go back. Simple as this. And here we can note that in order to assess the fitness, in our case, what we need to do is, okay, first of all, we encode the policy. We need to reset the environment, and then we need to run this loop of stepping the environment. I guess you're all familiar with the OpenAI Gym kind of interface for robots. Not really? Okay, so simply this is a pseudocode that represents that, but it's as any robot simulator, let's say. So for every time step that you simulate, you sample the observations, you take them, you decide what actions to make, and you feed these actions to the robot for it to make them. So we step to the following time step. And so this is the loop. And what we must note here is that to properly assess the fitness in evolutionary policy search, you need to run a full simulation of the robot, which is, not super convenient for certain perspectives, as we will see later on. So I started this with the case of discrete control. By discrete control, we mean those robots where the amount of actions are discrete. You can think of that as the Atari Pong, for instance. So, you have to move the paddle up or down. You can perceive a lot of things, but the actions are discrete. In this case, we add 4 scenarios, for robotic scenarios. Maybe you're more familiar with the mountain car, actually, which is also a physical problem, where you need to let's say, move the car back up the hill for you to be able to go down and come up another hill. And we compared it with DQN, which is the state-of-the-art, among the recent state-of-the-art for discrete control with neural networks. And we didn't do any parameter tuning for either of the approaches. Here we plot the reward on the y-axis, so being higher means being better. And we can note that, in general, CGP is never worse than DQN. So it's quite a good achievement. Must remark that no tuning was done, so a lot could actually happen if we tune the parameters properly. But the result is quite good. And as a bonus, we have the equations that we can clearly visualize. That is the cart and pole. That was the easy one. I should have made it an example, actually. Where you simply need to move the cart left or right in order to prevent the pole from falling. And we can see that we were able to extract the equations. This is the support, we call it, for the left action. This is the support for the right action. So whenever the left one is larger, it will go to the left, else it will go to the right. So we were able to, in fact, transfer this to a linear equation because only 2 of the variables of the pendulum were taken into account, the angle and the angular velocity. And we were even able to draw a decision boundary on the plane where we plot these variables. The problem is simple, so I wouldn't consider it as an amazing result, but still not disappointing. We can also do this for visual control, such as the Atari Pong that I was giving you as an example before. So what we did here is the same kind of setting, but the type of functions that we could use were also functions that were able to process images. And in this case, we used an enhanced version of CGP, where you have different types of functions grouped in different genomes. But again, it's a different way of optimizing a graph of operations from the image to the decisions. And what we noted here is that the performance, at least on the seeds that we trained the controller on, was amazing. So 21 is the maximum score that you can get in a Terrypong. You're all too young for having played that at the arcade, I guess. But I spoke to my supervisor, who is a bit, was like, yes, you can do 21 more. Okay. So after coming to a clear conclusion on that, we were like, yes. And besides the fact that we were able to beat my supervisor, pretty good, we were also able to understand what was going on. So we compare this to explainable AI that I was showing you before as an alternative tool that one could use to understand what's going on. And we can see that with XI, you can do occlusion maps, for instance, or RISE, that in both cases are going to tell you which pixels have been used for coming to the decision. And these two elements, let's say, we're telling you, yes, it's focusing here and there, nice, but it's not really telling you which, changes in the pixels are triggering what type of decisions. Conversely, we were able to obtain a pseudocode that was telling, okay, once the ball reaches the midpoint, we're going to start the decision making that was like this and that and that. I personally was not able to understand it super straight. It took a bit of iterations. The program, this was the simplified program, actually. So the program that came out was a bit messy, but still we were able to come to observe something that we were like, kind of makes sense. So this was also another interesting result. Moving on, we can also move to the continuous control of robots. So again, a type of robots where the inputs are numbers in this case, and also the outputs are numbers, generally multiple numbers. So the first robot that we consider is this thing that it's called swimmer. It's not called snake. That's such is life. And the input space is of size 8, so not so large, and we only need to come up with 2 control equations. And when we compared it to PPO, another state-of-the-art, let's say, for continuous control in this case, the optimization of ANNs for continuous control, we were able to do quite nicely. Again, no optimization of hyperparameters, so if you go and look it up online, there are cases where PPO can actually do better. But in the same kind of optimization and fine-tuning settings, we were able to outperform it, with the additional bonus that we were able to see what variables were taken into account for coming to the decision. In this case, it's a bit more complicated because we're dealing with numbers. So at least for me, that I don't know anything about the physics of this element, I was like, it's related like this and that. But one interesting conclusion that we were able to draw with basically zero knowledge of the thing is that when you control the left torque, T1, you need to have information from this side of the robot. When you control T2, you need to have information from the other side of the robot, which to me was an interesting piece of information that's, in other words, telling us, you need to properly coordinate your robot in order for it to swim. So that was a first very good result. Of course, there are issues. There must be issues somewhere. So scalability is a core issue. This is the Walker 2D. The objective is this thing is to go around. The input space this time is larger, and also the output space is much larger. And again, when we compare to reinforcement learning, here another algorithm, but for us it's just an optimizer for ANNs, let's say. We see that we tend to be seated a bit at the bottom of the box plot, because in general complexity it makes it hard to find a good controller that can actually do its thing. And we hypothesized that this could, was that a question? Okay. We hypothesized that this could be because of the reward, that it's really promoting the fact that the robot doesn't fall. And this really causes a local optimum. In fact, the policies found by CGP were very stable, but they were in fact just stable. So not really taking any risks in order to walk. So what we noted in simple terms is that our optimization was converging prematurely on something that was not the optimal result. It was a local optimum. So we tried 2 ways to address it. I don't know if I'm going too long with this presentation, so.
We have a total budget of 1 hour for the whole thing with questions. So far you're good, I think.
Okay, else I will bring the viennoiserie back to it. To keep you quiet and happy. Okay, so we tried 2 different ways to address this problem. The first one was curriculum learning, and it's, as the name suggests, let's say we're trying to build a curriculum of progressively more complex tasks in order to find stepping stones. So we want the robots to acquire progressive skills in order for them to actually be able at the final task. This was not done on the same setting of there, but it's, let's say, an interesting way that one could use to address premature convergence. We use this on a different setting. I will spoil this for you. It was done on Super Mario. So this is why we could use LLMs for this, because somebody came up with a very interesting fine-tuned LLM that could generate Mario levels. So, okay, we can generate infinite amount of Mario levels with different specifics. Let's try to generate them so that they're progressively more difficult. And we can actually train our agents from the agents that are, able to solve the simple course where it doesn't need to do that much besides running. But then we progressively complexify the task. We start adding obstacles, enemies, holes, and hopefully the controller, because we don't necessarily need to control physical robots. We can actually control other, video games, for instance. And so this is the idea until Mario is able to learn the complex behavior that will make it traverse any environment. So here we noted that we were interestingly able to get a better final performance. I wouldn't say that to be so significant, so we consider the completion ratio of the level, which is quite below 1, so not super good. But still, we were able to settle for a consistent result at the end. Conversely, if we only train on the most difficult levels for the entire budget of evaluations, in some cases, the results were comparable, in some others, it was worse. And in addition, we could get an interpretation of what was going on. In this case, we treated the visuals as a discretized grid and then processed it with encoding obstacles and enemies with different numbers. And what we learned from this is that it's using only the pixels that you show, the macro pixels that we show in white here. So what it does is that the majority of the time, this exponential is going to be pretty big. So the majority of time, it's just going to go. But when there is something here, it's going to jump, because it's going to trigger the action to jump. So more or less, we can still get an interesting insight of what's going on in the robot. The other way that we try to address premature convergence is quality diversity. And this is another optimization technique that doesn't only aim at optimizing solutions that perform very well, but it also optimizes a variety of solutions that perform hopefully well, but in different ways. So for the robots, you can think of it as robots that run, jump on the left leg, the right leg, and so on. So this is more or less the idea. But usually it's done on the behavior of the robots. What we thought it was to also diversify on the structure of the graphs, which could be a good incentive for interpretability. Because if I take a look at one graph, maybe it's very good, very high performing, but very bad for understanding. Maybe there is another one slightly less performing with different features, but much better for my understanding. So that brings our focus back to interpretability. So we built on Mapelitz, which is an algorithm that divides the total amount of solution in different niches. Each niche is characterized by a different type of descriptor. So for instance, you have the robots that touch a lot of the time with their right leg, the left leg for the behavior. Concerning the features of the graph, we decided to use the amount of 1 and 2 arity functions divided by the number of nodes total in the graph, which more or less expresses different things. So 1 arity functions are usually exponential, sinusoids. So those happen to be less easy to understand, and also they imply less connections. So it's kind of covers two aspects. Two-arity functions, often more simple to understand, but they imply, of course, more connections because you need two inputs to use them. And the division by the number of nodes tells us how many actual nodes are we using in the graph. So what we do is we take all of our solutions and we group them according to these features, the graph features and the behavior features. And when we do the optimization to create new solutions, we decide to sample from either of the archives or from both. So all of these are the variations in which we either sample from both, only from the behavior archive or only from the graph archive. And this was the solution obtained before. So if we don't see this one, we're like, interesting improvement. Of course, when we take a look at what reinforcement learning was doing, we're still not there. So this is another tiny step in the right direction, but possibly not the correct one. And what we can note about this one is this plot additionally is that when we focus on these two, let's say, they consider the behavior features for diversifying. And these are the ones that are really helpful for improving the performance. You can see that the jump is quite bigger. Conversely, when we focus on the diversity of graphs, we don't really have that much benefit in terms of performance. So it's possibly wiser to focus either only on the behavior if you don't care for interpretability, but that would be stupid because, otherwise you just go for an NNF. Otherwise, you just sample from both and you have hopefully the best of both worlds. Additional bonus that we could get is that CGP uses innately feature selection as any other GP technique. It doesn't necessarily use all of the inputs possible, which is already good because if a sensor dies and we're not using it, we're good. Additionally, if you have a lot of different policies that use different sensors because they solve the problem differently, if a sensor dies, you probably have in store a policy that was able to solve the problem quite well without using that. So this is what this plot is telling us. When we broke different sensors, the performance doesn't really decrease that much, at least the top of the plots. Still, some decreases, but not too bad. And as I was saying before, this was also born with the idea that we can additionally increase interpretability because we allow the user, the person that will decide whichever control gets deployed, to pick from a larger variety. So what I'm plotting here is the two archives above in terms of fitness. So this is the behavior archive. We're considering the robot that's walking like this, so contact of each leg on the two axes. Here, the descriptors for the graph. And it's like this because of some of the functions cannot exceed one. So this is why we can only cover this part. And we can see that in terms of fitness, they correlate quite nicely. So there is quite a gradient of color over there because CGP tends to explore more the region of small graphs. So this is why this area tends to also be fitter. Concerning the behavior, we see the typical trend where a quite equal use of the legs is a good idea. When we move to the interpretability, you remember the formula that I was showing you before, the one that accounts for different features of the equations. We can see that here it has a very nice scatter to look at, but not that much information. So when you want something that's yellow, so more interpretable, you don't really know where to look at. Conversely, when you take the archive that's diversifying on the graph, you can see that in general, the most interpretable formula will lie down here. So thanks to this correlation, we possibly have more expectations of where to go look for interpretable formula, and also more ways to foster them, let's say. So coming to very close to the conclusion, the current approach has some strengths. So it is quite good for interpretability, because we were able, for instance, to show decision boundaries, variable relationships. Pretty interesting. Also, it's not very sensitive to hyperparameters. We compared it to reinforcement learning, and we saw that we did not optimize hyperparameters, and the results were not awesome. It does implicit feature selection, which can in fact, increase robustness and generalization abilities. In case something breaks, there's some chance that we were not using it, so we don't really care for that. Of course, with strengths come also some limitation that belong mainly to these three macro categories. The first one being suboptimal performance. Okay, we have interpretable policies, but if they don't perform in a way that's satisfying, we are not really going to use them in the real world anyways. And also, not all of them were so clearly interpretable. As I was showing you the pseudocode for the Atari Pong, we were like, yeah, it's a pseudocode, but what is it doing? The ball. And we still had to do some post-processing in order to get to that pseudocode before it was even larger. And last but not least, this approach for optimization has much higher computational costs compared to reinforcement learning because it doesn't really have a high sample efficiency. Because of how the optimization was working, and I showed you before, you need to run an entire simulation to assess how an individual policy is behaving. So hopefully with these ideas, I will be able to fix it. I don't know. We will see. And for the first two problems, my idea would be to focus on policy modularity, because as I was stressing, it's a good point for interpretability. In general, human engineered systems are made of different blocks. And even if an individual block can be a bit larger, you can still give it a label, let's say, by saying, okay, this block is actually doing this. And you can kind of ignore it for the higher interpretation. So that's going to help us also for the interpretation, but also for the performance. Because if a robot needs to do a set of complex tasks, and you're able to identify the building blocks of these tasks, you have more chance to be able to evolve, optimize these small tasks, and then hopefully to combine them. Coming to the computational costs, the idea would be to take inspiration from reinforcement learning, which is known for being significantly more sample efficient than evolutionary optimization. So the idea would be, for instance, to focus on an actor-critic type of architecture. So the actor would be still interpretable, the critic will be trained in a much more efficient way. I don't know. Let's hope it works. Coming to the applications, I will only speak about one, which will be the topic of the postdoc. One of the topics of the postdoc that I will be starting from the beginning of next month, which will be a medical application. And you can take basically any control problem that you like and try to apply this approach and see if it works or it doesn't. I chose an application that's hopefully going to do some good to society. And in this case, it's a medical application where you have ICU patients, so patients that have, for instance, undergone heavy surgery or are in health-threatening conditions. And these patients are often attached to mechanical ventilation systems. So they're not able to breathe by themselves. They have these devices that control the flux of oxygen and a lot of stuff. Let's put it like that. And these devices have a lot of settings. I had no idea about it. I was speaking to these doctors and they really opened an entire new world for me. And these settings, what happens currently is that the doctors fix them every 8 hours, let's say, whenever they go and they pass to check the rooms. But possibly one can benefit from having them checked and updated more often, both for the health of the patient, but also for the less overload of the medical doctor. And the idea here would be there is already some data that's been collected in Toulouse by the university clinic, university hospital. And with that data, we hope to be able to build a digital twin that tells us how the patient behaves under different conditions. And with this, we hope to be able to train an interpretable policy that can tell us more or less what we should do in any setting. First of all, this will be probably used as an AI-assisted decision-making tool. So it will hopefully, again, be able to alert the doctor saying, we should do this and that. Soon there will be the need for this and that. Hopefully in the future, if the tool is really perfect and it can pass, all the trials and so on and so forth, it can even become an automated decision-making tool. We will see. I have hope for this, but as any research, we don't really know. So I guess, we're coming to a conclusion. I hope that the flow has been interesting to you, and of course, if you have any questions or suggestions, I'd be happy to hear.
Thank you very much. I have questions. If I can begin because I have wings.
Okay.
I have a first one about the complexity issue that you raised toward the end. The complexity issue is mostly a complexity for the training process, but not necessarily for the inference compared to reinforcement learning.
Yeah, totally.
Okay.
Totally.
And so did you compare how complex is CGP, for example, and if you allow the same budget of computation power for inference to SAC and to or PPO and to CGP, how does it compare?
I didn't really focus on it for inference, but I think we were comparing new evolution and this with the same amount of budget for both optimization and execution later. So in that case, you're running a neural network, so inference is the same in both cases, and the runtime was comparable. There were no significant differences. The implementation was done with the same optimized framework on GPU. So I guess that on runtime they're comparable.
Okay.
Possibly even CGP might be faster when actually implemented on a physical robot.
I have a question.
Yeah.
Thank you for your very good presentation. It's on the interpretability. You said that there was a bit of work from the raw policies when you finish the training to the interpretable policies.
Yeah.
Can you describe what's happening? Do you delete the constants, for instance?
So constants are actually a taboo question now because we're not optimizing them in the proper way that we should yet.
Okay.
So I think that should really be the very next step because it's silly that we're not optimizing them. But besides constants, what was happening is that often it needed to create, for instance, a constant. It was saying, okay, let's take the screen, make it black, take the pixel there and there just to make one. Because we were not having that.
Yeah.
Some other things that we were observing was operations that were not really doing anything, so we could remove them. So these types of settings.
Hitchhikers are okay. Because we have the same as DPG. There is a big mess that we get at the end, and going from that to interpretable. I have not tried, maybe Quentin did, but it's quite hard.
Yeah.
DPG.
Yeah, I must say that in this case, I was working with this other student, and it was him that took the rough part. So I was hearing, this policy really looked bad, but here's the pseudocode. And then he was giving an overview of what was going on. It was mostly that.
Did you try to use LLM to interpret the code?
I think he did.
Okay.
It's something that's fair as an idea, but then how do you know if it's not hallucinating? So trying to put something that's not interpretable on top of something that's interpretable could be a very reasonable starting point.
Maybe to make sense, and then you can.
No, totally. You should validate to see if
it's a valuable validation.
Yeah.
At least as a first step. If it would be able to find some insights of.
No, but I think it should be done. Yeah, that's a very good point.
Yeah, so just on the interpretability, because I have another question, but I don't know if when Camilo, who did the study on Pong and stuff, did he did multiple seed analysis? Did he analyze different model or only one? because I'm curious about like how the model is able to find different policies that were able to reach the maximum score. And like, I don't know if it's something that you studied.
Okay, this is not something that I did,
Yeah.
but it was something that they did in the team. Incidentally, I also ran a competition 2 times on these topics. And the second edition of the competition was to solve Pong in the best possible way. And this team, which was composed by the same leading student and also another master student there, they figured that Pong, Atari Pong, is composed of a set of 6, I think, or 5 different seeds in the end. So, for instance, seed 1 behaves very similarly to seed 7, whatever. So after a certain amount of time, they are recursively repeating. So what they did is they trained on a subset of those, something like that.
Okay.
And on some representatives maybe. And then they were able to optimize one single policy that was able to run well on all the seeds.
Okay.
So it was totally deterministic at the end, or?
Yeah.
Okay.
Yeah, the policy is
Which makes it
deterministic.
easier.
Yeah. TPG is not deterministic, or?
Yeah.
No, I was talking about the
environment.
Pong.
Okay, yes. They figured that there is some determinism. It's not meant to be. You still have the frame skip.
Yeah.
So if you're familiar with that, you have the probability of missing one observation every 4 or not properly doing the action 1 every 4. So that still makes it stochastic. But in terms of the simulator behavior, it's cyclic.
And I was curious about the idea of using a critic network to train JD programming.
Yeah.
So it's like the idea is that, right? So I'm curious about like what the critic network would do.
Yeah.
Basically, like, have you already a plan in mind?
Yeah. So there is this work that was started by a team in Brussels. And what they did is they took, I think, was an interpreted algorithm
or something like
yeah, I think it might have been D3, and they ran the actor. They collected all of the transitions, and then from that they took the critic that I think at the beginning it was from scratch, and then they kept optimizing on the. I don't remember it well.
Okay.
It was
Okay.
done. But then they were using the critique in order to steer the actions towards something better.
Okay.
So if the actor was outputting 3, maybe it should have been 3.5 according to the critique. So then they were doing regression in order to move the actor again to that.
Okay.
And they were doing it cyclically in order for the critique to stay well anchored to how the actor was behaving. Spoiler, it was not really working.
Okay. Okay, so it was still kind of a different critique as a classic critique that you have in deep reinforcement learning.
It was still an ANN as a critic.
Okay.
So the idea was more or less the same.
Yeah. Okay.
Yeah.
Okay.
But they were not able to make it work yet. I started trying to work with them. They also used CGP at some point, but they didn't give many good results. I guess the main problem is that it works super well for representations that are very local. So you can move a tiny step in a certain direction. With this one, when you do mutation, you were here, you might be here, here, or here. That's the problem, I guess.
Okay.
We still have 1 or 2 minutes for questions. If there are some questions online, you can just open your microphone and talk. Otherwise, we can still take questions in the room.
Yeah.
That's one question. You were talking about simulated users and then real users to evaluate interpretability.
Yeah.
How does that work? I have no idea.
Yeah, okay. So I was very fast on that. So, of course, the idea is that, first of all, you need to encode your neural network to feed it to the estimator. For instance, you take the neural network that you're going to train, and you need to encode the neural network to make it a sequence, basically. We were using classical neural networks back then. We didn't have transformers and stuff. So it was, transformers were a thing, but it weren't that popular yet. So you need to encode your neural network, your formula somehow. And within that encoding, you can also assign certain weights to certain elements in there. So for instance, you weight a plus symbol 3, a minus symbol 2, something like that. And you get to an overall number that can quantify how much the interpretability of that formula is. It's not going to be a necessarily good estimation, but it's still going to be coherent. So that was mostly to see if we were able to train an estimator to actually grasp that, and that was proved to be feasible. And then if the different approaches that we were using, so for instance, different weights for different operations, different sizes of formula and so on, if that was giving different types of optimization, let's say if it was steering the optimization in different ways to giving different results.
Okay, but you simulated user you were not trying to simulate a proper user more than creating fake user which would have different preferences.
Yeah, it was more like fake feedback, let's say, like artificial controlled feedback. I think that we should do it again with an LLM now that we have this, but every study should be done again with an LLM.
Talking about the energy and
yeah, exactly, you know.
fast or slow.
Yeah, exactly. Energy, money, and water.
Okay, well, the time is over, so unless there is a very last short question, let's thank our speaker again. Thank you.
Thank you.